Go. The location for tomorrow evening, final part 2, Sterlington, LO11. Now, let's complete our conversation on stereoisomerism of transition metal complexes. The last type of stereoisomer that we'll talk about, diastereomers. We defined such last time. Interesting geometric isomers. Because they are each optically active, but they're not mirror images of each other, even though they're isomers of the same compound, therefore have the same formula. Simplest example of such, using monodentate ligands, would be this octahedral complex. 2 identical A ligands, 2 identical B ligands, and a C ligand and a D ligand. All cis. Again, if an isomer is to be optically active, it will be the isomer of lowest or least symmetry for the complex in question. All cis corresponds to that. These each have mirror images which are different from the object itself. The mirror image of this is different from this. The mirror image of this is different from this. But these are not mirror images of each other. And the mirror image of this and the mirror image of this are not mirror images of each other. These are examples of diastereomers. You will look at such molecules in organic chemistry class. You will also look at molecules from a isomeric standpoint known as mesomers or mesocompounds. Interesting. In one molecule, you'll find 2 optically active sites. 2 chiral atoms, likely carbon atoms, because you're talking about organic molecules in organic class, of course. But a mesomer itself is not optically active, because it creates an internal mirror image of itself. The 2 chiral carbons will show this. I don't know of transition metal complexes which show this behavior, so we'll not consider such. I just passed that as a comment, about which you'll hear, of course, more in organic class. But diastereomers, of course. These 2 ligands look familiar? Did I ask you to think about these 2 ligands on this bonus quiz? If, for example, we get rid of C and D, and replace C and D with this chelating ligand, where N is a donor atom, and the sulfur atom at the other end is a donor atom, we can create another example of diastereoisomerism. These are each optically active, but they're not mirror images of each other. What happens to the complexity of the stereochemistry of a complex if you use this as a chelating ligand? I asked you to think about that in this bonus quiz. since it's related, obviously, to what we are presently discussing. What do you got to say? What did you say? We'll find that out later. Did you recognize that this nitrogen atom is chiral? Let's expand this formula. We don't need to expand the CH2 parts. These are each chiral nitrogens. So when you use a ligand like this as a chelating ligand, clearly you must have a complex which is optically active because this ligand is optically active. So that will increase the complexity of the stereochemistry of the stuff considerably. If I put this in here, woo! Now I got all kinds of stereoisomers to consider. I wouldn't ask you to draw pictures of all such things on an exam, but I would ask at least, if I choose to ask about something like this, I would ask at least that you recognize the complexity of the problem. Another example. With models. Here, for example. Clearly, this portion of this complex, the silver thing, represents the complex metal. And you see 6, 1, 2, 3, 4, 5, 6 coordinate covalent bonds connected to this complex metal. This is a chelating ligand. A chelating ligand like this. A chelating ligand which is optically active because of this atom, which is connected to these skeletal atoms, and these peripheral groups which are different from each other, like the methyl group and the hydrogen atom connected to that right side nitrogen. This, of course, is stereochemically very simple. All these ligands are the same. Nevertheless, this thing is guaranteed to be optically active because this ligand is optically active. This look like the same thing? Be careful when you're talking about isomers with the phrase same thing. Because clearly this, at the minimum, has the same formula as this. So if these are not exactly the same thing, they're isomers. What kind of isomers are they? Well, let me take this thing and hold it like, whoop, there we go. Hold it like this, okay? Here's the mirror in the middle. These white donor atoms, the large white donor atoms, part of the chelate ring, not the small whites, which all represent monodentate ligands, of which there are 4 in each complex. Like monodentate ligands throughout. Okay? Does it look like mirror images? These are mirror images of each other. Now then, let's take a look at what we have on the board with the model. Now, I've got to be careful in using these models. They're nice models, but they're very fragile. Whoever made these, if they would have just improved the design somewhat, would have been so nice. But these things break easily. And then teacher gets mad. That's not good when teacher gets mad. All I'm going to do is act on this chiral donor atom, which for what we have on the board is a nitrogen atom. Let's take this, which represents a hydrogen atom, this, which represents, for what we have on the board, a methyl group. Put the valves over there. What have we got now? Have we now turned these things into identical complexes? What do we got now? Are they mirror images of each other? No. Well, let's see if they're superimposable. Oh, geez, how am I going to do that? Let's try this. Reds, reds, blues, blues, whites, 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 whites. But look what we got here. A monodentate and a chelate ring donor atom. Same thing over here. Chelate ring donor atom, monodentate ligand. Not superimposable. Again, they have to be optically active because of the chiral atom on the chelate. What would we call these isomers? Diastereomers. Another consideration related to this, I believe you talked about this at least to some extent in discussion class. Let's look at these two nitrogen atoms. Are they equal in donor strength? Exactly so. I ask this because the related issue that you discussed in discussion class on Friday was this. Remember that? Ammonia molecule, ethylene diamine. Clearly, they have to be very similar in their sigma donor strength abilities because the donor atoms are all nitrogens. They're exclusively sp3 nitrogens. So orbital electronegativity regarding the donor atom has no bearing on the issue. And this nitrogen is covalently connected to 3 hydrogen atoms, whereas this nitrogen is covalently connected to 2 hydrogen atoms. And instead of all 3 NH bonds, this has an NC bond. How does the polarity of an NC bond compared to that of an NH bond? They kind of close? Are the electronegativities of hydrogen and carbon kind of close?
Yes.
Kind of close. Hydrogen, you remember what the electronegativity of hydrogen is on the Pauling scale? 2.1. Carbon 2.5. Now then, that suggests that carbon, from an atomic electronegativity standpoint, is electron withdrawing relative to hydrogen. because carbon has a higher electronegativity than hydrogen. That would support the conclusion that ammonia is a more effective sigma pair donor than the nitrogen atom on ethylene diamine. But since neither of these ligands is capable of pi bonding, we can get a handle on their sigma donor strengths by looking at the ability, the compared ability of these two in behaving as Bronsted bases. We can get that information from our acid-base table. Regarding this, I told you to look at the acid-base table for these two. What did we find out? We find out that Kb ammonia is 1.8 times 10 to the minus 5. We'll rough it as 2 times 10 to the minus 5. Whereas Kb for this is on the order of 8 times 10 to the minus 5. So as we knew before we looked at the numbers, they had to be very comparable in donor strength, but the data show that the nitrogen for ethylene diamine is a little better donor. That doesn't keep with the atomic electronegativity assessment that we made a moment ago on the basis of carbon being more electronegative than hydrogen. So we got to look past atomic electronegativity. Remember, when we started to develop considerations which we would use to rationalize strengths of Bronsted-Lowry acids and bases, we found there were a lot of factors. You need to have all these factors in your memory banks so you know what factors to think about. But oftentimes, 2 or more factors applied to the same case compete with each other. They fly in opposite directions. For example, as a reminder, when we looked at the Bronsted acidity of the hydrogen halides, HF, HCl, HBr, we found out that since the acid strength trend is to increase from the top of the family to the bottom of the family, in fact, of the hydrogen halides as acids, HF is the only one of these that's a weak acid. The other are all categorically strong acids, with HI being the strongest. So the argument we came up with that supports this was stabilization of negative charge density by the conjugate base as a consequence of charge to size ratio or electronegativity. Which fit? Which of these considerations fit the facts? Charge to size ratio. But when we looked at the relative acidities of an in-period related series of acids, CH4, methane, H3N, ammonia, water molecule, HF. Well, we know from the acid-base table that HF is a much stronger acid than water. That doesn't mean it's a strong acid, but it's a much stronger acid than water. And ammonia, we have recognized, shows behavior in water solution only as a base, not as an acid. So if we establish a trend from this information, we will expect for methane, ammonia, water, and HF that HF is the strongest of these 4 acids and methane is the weakest, which is correct. So we looked at their conjugate bases and said, what rationale can we apply to recognize that the effective negative charge density of the methide ion, that's H3C with a minus charge, is the greatest for these Bronsted bases. The methide ion is the strongest of the bases derived from these acids. Did we rationalize this on the basis of charge to size ratio or electronegativity? Do you remember? Do you remember we're going to ask you about this tomorrow night? Well, methide ion is certainly larger than F minus. So on the basis of charge to size ratio, we would expect methionine to be the weakest and most stable of these bases, because the charge to size ratio is the smallest. They're all -1, but methionine is the largest. Does that fit the facts? No. Methionine is the strongest of these 4 bases. So now we pay attention to electronegativity. Did that fit the facts? Yeah. Expect F- to be the least reactive of those 4 bases, the most stable of those 4 bases, because F- is derived from fluorine, the atom of greatest atomic electronegativity. Just reminding you about stuff we already talked about. So again, when we looked at these 2 cases, which you did Friday in discussion class, you said, well, based on atomic electronegativity, this should be a somewhat more stable non-bonding pair than this, because carbon has a higher atomic electronegativity than hydrogen. That would make this a weaker base and a poor sigma donor. But this is a stronger base and a somewhat better sigma donor. So the atomic electronegativity argument is no good. So, you said, how about this? Remember what that is? Orbital electronegativity. Hydrogen has only 1 orbital available for any of its bond formation interactions. A 1s atomic orbital, that's it. This carbon is an sp3 carbon. And the s and p orbitals to create this sp3 hybrid are from energy level number 2, because carbon is an atomic member of period 2. How do you expect the orbital electronegativities to compare for a 1s atomic orbital and an sp3 hybrid derived from the orbitals of energy level number 2? Hey, you cannot, as an electron, be more stable than being in a 1s orbital. That's right next to the nucleus. No electrons between you and the nucleus at all. So based on orbital electronegativity, we reach the conclusion that this is electron releasing relative to this. Electron releasing, or electron density releasing if you prefer, which makes this non-bonding pair more reactive. Does that fit the facts? You betcha. This is the more reactive molecule. It is a stronger Bronsted base. So now you've recognized that if I have a hydrogen atom connected to a donor atom, and for an identical donor atom, instead of a hydrogen atom connected to it, I have a methyl group. Isn't that what we got here? This nitrogen atom is connected only to hydrogen atom. This nitrogen atom connected to a hydrogen atom, but also a methyl group. Which one of these nitrogens is the better donor atom? Based on what we have come to know about the properties of ethylene diamine versus this. Which of these is the better donor atom? This nitrogen or this nitrogen? Because the methyl group is electron density releasing compared to hydrogen. Which is the better donor atom? The left side N or the right side N? This guy. Stuff about which you'll be asked to think on a very frequent basis in organic chemistry class. You'll find out that carbon atoms, rather than nitrogen atoms, since in organic you're talking most about carbon atom chemistry, a carbon atom which bears a negative charge is called a carbanion. So when we talked about taking H plus from the methane molecule, you create this carbon anion, carbanion. Carbanion, one word. All right? And you will find out that if, for example, one of these hydrogen atoms is replaced with a methyl group, you've increased the reactivity of this minus charge. You've made this carbanion more reactive than this carbanion. Now even more so. All follows from what we have considered today. All right, enough on that. And now, let us proceed immediately following chelate effect, which you talked about in discussion class, and which led us to this consideration on ethylene diamine versus ammonia and this substituted nitrogen for ethylene diamine. Let's go to page 2418. Stability of the chelate ring. Stuff which you have been asked to think about previously. Again, ethylene diamine, which converts to this if we operate on this chemically and remove the CH2 groups. This simple molecule, whose name is hydrazine, has two potential donor sites. It's got two sp3 nitrogen atoms, each which bear a non-bonding pair. Just like this. Now, when this does its chelating thing, you get a 5-membered ring. So regarding that 5-membered ring, we had a model of the ethylene diamine molecule, like this. And this, for this model, the purple ones simulate carbon atoms, and the blue ones simulate the nitrogen donor atoms, and the green things simulate hydrogen atoms, and the shorter sticks to the green things are a consequence of bonds to hydrogen atom being a good deal shorter than single bonds between larger atoms. And you recognized, or asked to reconsider a bond property that you learned about, or a property of single bonds that you learned about in Chemistry 2045. At least I trust you learned about this. Which is that along the axis of a single covalent bond, the connected atoms or groups can rotate in directions in space opposite to each other without breaking the bond. You cannot do that if at a covalent bond site you have any degree of multiple bond electron density. Then the free rotation property is lost. So that's one way by which, by doing molecular studies with appropriate gadgetry in the laboratory, we can find out if we're talking about single covalent bonds as opposed to covalent bonds which have any degree of multiple bond character. In any case, when it comes to chelation, because of this free rotation along single bonds, this thing can orient itself such that the non-bonding pairs on the two nitrogen donor atoms point at the same position in space, which accounts for why this thing is capable of forming a chelate ring. So I like to chelate my noggin. My noggin is now a metal ion. And this gives me one of my very beautiful Easter hats. Okay. Sorry that the chelated metal ion isn't all that pretty itself, but the chelate ring, you must admit, is quite pretty. The hat. Okay. And then, if you simply count the number of atoms in this ring, you got the 2 nitrogen donor atoms, the 2 skeletal carbon atoms, and my noggin, that's 5 atoms. Ethylene diamine is by far the most common and best known chelating ligand. If for no other reason, it's the simplest. Okay? And so, at the time at which you first looked at this, at least of the discussion people asked you, one of the things I wanted to ask you, was to count the atoms, 5, and recognize that this corresponds to a stable chelate ring. All right? Let's go back to what we have on the board. Again, if I can go to laboratory, or if I go to laboratory, and synthetically remove the 2 CH2 groups from the skeleton of this molecule, I turn it into this molecule. This is a known stable molecule. It's called hydrazine. If this thing behaved as a chelate, there's the ring you'd get. And coordinate covalent bond, coordinate covalent bond. But we never get chelate rings like this. At least I don't know of any. Why not? Another piece of information that relates to this. Again, a lead in to some of the stuff you'll do in organic chemistry class. These are each sp3 carbons. This is a 3-atom ring. Carbon, oxygen, carbon. This 3-atom ring is known as an epoxide. A special kind of ether. Never mind the fact that it's an ether. You'll talk further about functional group recognition and stuff like that in organic class. What we want to recognize now is that this 3-atom ring is particularly reactive. It's very reactive because the ring is very unstable. This ring very easily ruptures, which relates to why I can't make this chelate ring, which relates to why this cannot behave as a chelator. It can be a monodentate ligand, but not a bidentate ligand, at least not to the same metal atom. Why do you expect this ring to be very fragile, reactive, difficult to form, and if formed, very easy to break? Well, the organic folks pardon me, discuss this problem by referring to it as ring strain. Strain rings, as implied by the word strain, are quite reactive, fragile, easy to break. On what basis might we expect this 3-atom ring to be fragile and easy to break? On what basis might we expect it to be impossible to form this chelate ring? Why is this 3-atom ring unstable? Why does it have severe ring strain? Well, as this Lewis picture shows us, these atoms are each how hybridized? sp3. What kind of bond angles do you generally associate with sp3 hybridization? 109 degrees, more or less? What kind of bond angles you got for this ring? I'm sure you all did some plane geometry in your high school math. Triangle, sum total of degrees in a triangle, 180 degrees. So if these ring angles are all the same, each ring angle is 60 degrees. That's almost half of 109 degrees. Well, what does that do to these bonding electron pairs? Or put another way, you think the bonding electron pairs between carbon and carbon and carbon and oxygen again, you think these bonding electron pairs are at 60-degree angles with respect to each other? Do you think these bonding electron pairs would repel each other quite severely if they were at a 60-degree angle with respect to each other? Hell yes. And repulsion among and between the bonding electron pairs leads to a great deal of stabilization. All right? Now, what do we know about the lobes of an sp3 hybrid? They're oriented in space at 109.5 degrees with respect to each other. That's the lobes of the hybrid, which accounts for why the bond angles expected for an sp3 hybridized atom are on the order of 109 degrees. Well then, if I draw a picture of the lobes used for bonding, which overlap with each other, not a very good picture. Then I'm going to draw lobes, oops, not very good, which have an angle of about 109 degrees with respect to each other. Well, if I do this, pardon my lousy artwork, the picture you see in the notes is a lot better. The picture to which I refer is shown to you on page 2419. Look where the overlap region is. Over here. Over here. Over here. Well then, we have recognized that a stable sigma bond has the bonding electron pair on an imaginary axis immediately between the nuclei of the connected atoms. Oxygen atom nucleus, carbon atom nucleus. Here's this imaginary axis, but the bonding electron pairs over here, far away from this imaginary axis, and consequently not effectively stabilized by these nuclei at all because it's far away. But these bonding electron pairs have to be far away because if you try to put them here and here, the repulsion between these bonding electron pairs would be very severe. Upshot, this is not a stable ring at all. It's highly strained. So even though the ring itself shows 60-degree angles, from a theoretical standpoint, we recognize that the regions in space where the bonding electron pairs are found is a far distance away from this imaginary axis interconnecting the nuclei of the bound atoms. Upshot, the bonding electron pair is not very stable at all. Result, the ring is quite reactive and easy to break. So we don't get these 3 atom rings. Well then, let's imagine we can go to the laboratory and take away one of these CH2 groups. Now, for reasons of nomenclature, you'd find out in organic class that if this is ethylene diamine, with this being an ethylene group, this would be methylene diamine, because a single CH2 group intermediate between 2 different atoms is said to be a methylene group. This would be methylene diamine. To my knowledge, methylene diamine doesn't exist. There are other reasons why I can't make this, but let's consider methylene diamine as a potential chelator. Now, if methylene diamine makes a chelate ring and the complex is octahedral, what kind of bond angle do we find at the position of the metal ion? We've looked at octahedral complexes many times now. Here's where the metal ion is. Another pictorial representation. Here's where the metal ion is. What kind of bond angles do we find for this thing? 90 degrees. Or 180 degrees, but the 180 degree consideration doesn't apply to chelation. Because remember, chelating ligands with simultaneous or nearest neighbor donor atoms interconnect cis coordination positions, not trans. So, when we go to a 4-atom ring, if we imagine, to simplify the geometry, if we imagine this to be planar, how many degrees contained within? You did this in geometry class. 3-atom ring, triangle, 180 degrees. How many degrees do you add to this polygon when you add an angle? How many degrees do you add? How many degrees do you add? 180. This, with identical bond lengths and all 90-degree angles, would be a square. sp3, sp3, sp3. Preferred bond angle, 109 degrees. We're still 20 degrees short. Upshot, we don't make any of these 4-atom rings. This leads to why a chelating ligand, one which we've talked about previously, like oxalate ion. If I have oxalate ion in solution, clearly it can be approached by a metal ion coming this way or a metal ion coming this way. These are just particles swimming about helter-skelter in a solution. If I expect oxalate ion to do a chelating job, to chelate with the metal ion, could I form a stable chelate ring if the oxalate ion approaches oxalate ion in this end-on fashion? Because if the metal ion approaches oxalate ion in this end-on fashion, I'd have 1, 2, 3, 4 atoms in the ring. But if the metal ion approaches here, and I get chelation with this oxygen and this oxygen, rather than with this oxygen and this oxygen, then I'd have 1, 2, 3, 4, 5 atoms in the ring. So here, with the side-on approach, I find oxalate ion doing its chelating thing. Not this way, but this way. Here I get 4 atoms in a ring. Here I get 5 atoms in a ring. Stable. So let's take a further look at our 5-atom ring formed by oxalate ion or ethylene diamine and bunches of other ligands. Okay. The donor atoms as well as the skeletal carbon atoms are all sp3. "90-degree angle where the metal ion is. If it's an octahedral complex, what kind of hybridization do we find for the metal ion? sp3d2? Is there another possibility? If the d orbitals are lower in energy than the s and p valence orbitals, then it's d2sp3. Okay? Now then, if I imagine, from a geometric analysis standpoint, that this 1, 2, 3, 4, 5 atom ring is planar, how many degrees are contained within the ring? 540. I added an angle, I add 180 degrees. All right, let's do some arithmetic. $90-degree angle, where I find the middle line. So 1, 2, 3, 4 remaining bond angle sites. How many degrees will this give me per bond angle site if I consider this ring to be planar? Watch out, there's a really tough arithmetic here. What's this equal? I'm listening.
12 and a half.
Now that's pretty close to 109 degrees, isn't it? But, is this ring planar? Back to our model. Now, when I've got both non-bonding pairs aiming at the same geometric position in space, I examine all the atoms in the ring. Okay? There's my noggin. I'm now holding this chelate ring side on, so you can look at all the skeletal atoms. The two purples, the two blue ones, and my noggin. Are these atoms all in the same plane? Are they in the same plane? Yes or no? You think so? Mm-mm. They're not in the same plane. Kind of close, but not in the same plane. For example, these things, not enough hands. Okay. Okay. If you look at this closely, you will see, at least if I hold a model like this, that the chelated atom is down here. And my nose is. So the 5 atoms together, which form the chelate ring, are not in the same plane. Now then, what do you do to bond angles if you take this pentagon and imagine that the skeletal atoms, imagine that the component atoms of the ring are all not in the same plane. Does the bond angle stay the same? Well, let's take a look at what happens to a bond angle. Imagine we have an atom here, an atom here, and an atom here. Well, this would mean 180 degrees if the atom is here, if the atoms are here, here, and here respectively. Now, if I deform this thing from planarity, doesn't make any difference how I do it. What's going to happen to bond angle? Is it going to stay 180 degrees? No, it's going to get less than 180 degrees. The organic folks have a simple term that refers to this. A non-planar ring has smaller angles than you would find if the ring was instead planar, and so they call a non-planar ring puckered. You could imagine the same thing with lips, if you wish. Lips, 180 degrees. But you meet up with your paramour. You want to have a kiss, so you'll pucker. And all of a sudden, the lips are not 180 degrees anymore. Just like this. So, we'll write down puckering of the ring reduces bond angles to 109.5 degrees. Just right. Well, let's go back to the laboratory with ethylene diamine and add a CH2 group. This is a propylene group. So this would be propylene diamine. This is a known ligand. Again, I don't care about the name. But since it is different from ethylene diamine, which we have referred to in shorthand notation as EN, and this is propylene diamine, we'll call this PN. Okay? If this thing does its chelating thing, then I've got 6 atoms in the ring. N, C, 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 N. The skeletal atoms of the ring, all sp3. All ring skeletal atoms are sp3. If this is part of an octahedral complex, then we got a 90-degree angle here. So we'll do some arithmetic like we did over here. Except that now, if we start by treating this as a planar surface, how many degrees contained within? If planar, how many degrees inside? 720. So we'll go with 720 less 90 divided by 5 this time. All right? What's that give us? 126. Now that's a good deal larger than 109 degrees. That would lead to ring instability. But let's make the model and see what in fact we do have. I've added a CH2 group to the skeleton of ethylene diamine and turned it into this thing, propylene diamine, of which we have a picture on the board. All the covalent bonds are single, so along each covalent bond axis we can have free rotation, which, as is the case for ethylene diamine, allows this thing to convert itself to a structure which will have both non-bonding pairs aiming at the same position in space. Now I get an even fancier Easter hat. Okay? Now, when I look at this ring side on, can you recognize that it's not, the skeletal atoms are not exactly in the same plane? Puckering again. And by puckering, as it is the case with the ethylene diamine ring, we wind up with bond angles that are just right for sp3 hybridization. Now for this stuff, let's finish with one additional consideration. Ethylene diamine. Let's go to the laboratory and do some more chemistry on ethylene diamine. And turn it into this stuff. Or with further chemistry, turn it into this stuff. Pictures on your notes. Lewis pictures for each of these right now. For each of these molecules, we'll ask the question, chelators. What do we think about the ability of these molecules to form chelate rings? Clearly, they've got 2 nitrogen donor atoms. So in that regard, they can be chelate rings, chelate ring formers. Well, what do you think about the actuality of this? What's your Lewis picture analysis tell you? What bond properties did you find for this molecule? Not shown by ethylene diamine. What bond properties did you find for this molecule? Not shown by ethylene diamine. What did you find out? You find this? Here, we got a carbon-carbon double bond. Only single bonds in ethylene diamine. So now, we're looking at stereochemistry for the ligand itself. Because there's no free rotation along a bond axis which has multiple character. So here, this could possibly be a chelator because the nitrogen donor atoms are on the same side of the double bond, but not this. This couldn't possibly be a chelator. What names would you call these? Cis? Trans. Actually, the organic folks have better names than cis and trans for this kind of stereochemistry that's shown with respect to multiple bonding. But we'll let you learn about that in organic class. But, could this be a chelator? Yeah, because I got 2 nitrogen donor atoms. But can this be as effective a chelator as ethylene diamine? If so, why? If not, why not? And then how about this one? Whoops. No. How about this being a chelator? Now we got a carbon-carbon triple bond. sp3 nitrogens, but sp carbons. If you could see this molecule, what geometry would it show you? Planar? Better than that. Linear. Can this be a chelator? How would you ever close the ring? Impossible. Now back to this. What can you say about the effectiveness of this thing being a chelator compared to ethylene diamine? Well, if I put that thing in here, where these are sp2, then I'm going to fix these bond angles at 120 degrees each. So, if I treat this thing as planar, I have 540 minus 240 minus 90 for this. 120, that's 240. Divided by the 2 remaining bond angle sites. What's this going to give me? 300 less 90, 110, 210, divided by 2, 105. Now I'm starting to get a little bit of ring strain. And when I get to this, impossible. So, this really winds up being another example of what we have said many times this term. The most important property of any molecule is what? Structure. And that's what we looked at. We'll pick it up from this point tomorrow and offer our last